Hi, thank you for coming to see my video. My name is Jinsoo Kim and I'm from Post-Tech, South Korea. I'm going to talk about tactile sensation, felt as if it was passing through the body, which can enhance haptic experience in virtual reality. This work is done with my collaborator, Seungjae, Chaeyong Park, and my advisor, Seungmoon Choi. In the real environment, when contact occurs between a user and an object, we can acquire information about contacts through the kinesthetic and tactile cue. However, these kind of cues are not provided in VR, which limits the user experience and usability. Moreover, it is not always possible to provide exactly the same tactile cues as in the real environment for each virtual object, and it causes the hand to pass through a virtual object in VR. Tactile rendering of the sense of penetration can present the existence of a virtual entity, the sense of self-motion or object motion, and the sense of presence. Artificial tactile sensation, substituting real-world tactile experiences, is required to improve usability and immersiveness in VR. Therefore, we provide a metaphoric, plausible, non-painful penetrating vibrotactile sensation, experienced as passing through the body by using phantom sensation. The human brain perceives two nearly synchronous vibrations in close spatial proximity as one stimulus from a single source. As a consequence, we perceive an illusory tactile sensation between the two real actuation points, which is known as the phantom sensation. Here, an illusory tactile sensation is felt between real actuation points, and the illusory sensation can be moved if the amplitudes of vibrations are temporally modulated. Such moving tactile phantom sensations was verified for many instances, such as with vibration actuators directly stimulating the skin, within a physical medium that propagates vibration, and even outside the body, with and without physical medium. To the literature, we add a new type of tactile phantom sensation that moves across the opposite sides of a single body part. To embody a penetrating illusion for each body side, we extensively explored the control space of moving phantom sensation. We designed wearable vibrotactile displays for the two body sides of hand and torso. For the hand, we put two vibration units in a knitted glove. Each unit is in contact with the palmar and dorsal side of the hand. The vibration unit had a voice coil actuator inside, which was enclosed by a 3D printed cylinder-shaped cover. We selected the vest as the form factor to present vibrations to the torso. Two voice coil actuators were placed on the front and back of the vest. We tested the effects of the two constraints, stimulus duration and penetrating direction. To analyze the effect from the duration of the stimulus, half second and 1 second were tested. We also tested both directions of penetration. We used three vibration frequencies, 40, 100, and 250 Hz, to cover the entire range mediated by the two rapidly adapting mechanoreceptive neural channels, RA1 and PC channel. In the literature, various amplitude modulation methods have been explored to elicit illusory moving tactile sensations. In this research, we parameterized the vibration amplitude with the degree of polynomial gamma. Changing the degree of polynomial produces various mathematical functions, including those similar to log and exponential profiles. In this experiment, we used a four-factor within-subject factorial design. The four independent variables are the degree of amplitude function gamma, the duration of the stimulus, the frequency of vibration, and the direction of penetration. Gamma determines the speed of modulation, and its range was selected after pilot experiments. To assess the feel of passing through tactile sensation, we designed 3 evaluation measures. Participants were directly asked if the illusory tactile sensation feels like penetrating the body, and if the direction of such a tactile sensation is clearly perceived. Lastly, we questioned whether the tactile sensation is well matched to the visual information. For MANOVA, the direction of penetration was not significant for any measure. For simplicity, we pooled the data of different values and showed the mean scores of the 3 measures. For penetration, longer stimuli improve the illusory feel of passing through. It can be maximized by choosing an appropriate amplitude modulation rate, gamma. The best value for gamma depends on vibration frequency and duration, but using linear or larger values is advantageous. From direction clarity, an interesting pattern about stimulus duration is found for 100 Hz. In the half-second data, the trend of 100 Hz data followed that of 40 Hz data. However, in the 1-second data, the trends of 100 Hz and 250 Hz data were similar. The trend of harmony were very similar to those observed for penetration. In each stimulus duration, the harmony score of the 100 Hz conditions was the highest. A good phantom sensation per penetration is the ones with high scores in both penetration and direction clarity. Those in the top right corners in each plot. As the data goes off the diagonal to the top left corner, they represent the sensations that clearly notify the direction, but do not feel like penetrating. In contrast, the data distributed in the bottom right corners felt like penetrating, but had high ambiguity in perception of direction. All in all, the data should not go off the diagonal line of the perceptual space between penetration and direction clarity. The modulation functions represented by gamma most significantly influence the experience of sensory illusion. The fast-growing modulation, gamma from 0.25 to 0.5, were not the best option for the penetrating illusion. As the modulation became slower, from gamma from 1 to 4, the feel of penetration was apt to improve. We recommend slowly growing modulation functions with 40 and 100 Hz to present the sense of penetration. As the second experiment, we tested penetrating sensation rendering for the torso. The 2 experiments had essentially the same design except for the body side. For MANOVA, the stimulus duration was not significant for any measure. Therefore, we present the mean scores of the 3 measures from the pooled data of the 2 durations. Although the main effects of penetrating direction was significant, the mean score difference between the 2 directions was only 1.93. As it did it in the hand, 100 Hz was generally the best frequency to elicit passing through sensations. We observed the best penetration scores with the linear modulation, except for the 250 Hz and ventral to dorsal condition. The mean clarity scores of the 100 Hz conditions were higher than those of the other 2 frequency conditions in general. The penetrating sensation presented by gamma of 2 resulted in the highest clarity score for all vibration frequencies and penetration directions. Like the hand, the harmony scores were also very correlated with the penetration scores for the torso. the mean harmony scores of both 40 and 100 Hz conditions were significantly higher than for the 250 Hz condition. For penetrating phantom sensation to the torso, gamma and frequency were the two most significant factors. Penetrating tactile sensation rendered by fast-growing modulation were not effective for any frequency. Using a higher gamma is recommended. For the torso, the best penetrating experience was achieved by the linearly modulated 100 Hz stimuli, where the penetration field is clear without losing the sense of penetrating direction. In this section, we present a comparison between the results for the two body sides. If we compare the plots for the two body sides, the results for the torso are more scattered, suggesting that the effects of the independent factors were more apparent. For the torso, the tactile experience from the 250 Hz stimuli was not as good as for the other frequencies. We suspect that such weaker tactile experiences are associated with the propagation of vibration through the skin. The transmissibility of vibration is lowered as the frequency of vibration increases. This effect might be more significant in the torso compared to the hand because mechanoreceptors are much less populated on the torso. Finally, we suggest 4 design guidelines as to tactile phantom sensations that feel like penetrating. First, as we mentioned before, there were no noticeable differences between the two penetrating directions. When designing a penetrating stimulus, it is not essential to take direction into account. Second, stimulus duration is determined by penetration events. For the hand, the duration should have higher priority when deciding control factors. In our experiment, we found a reasonable difference in the subjective ratings between the tested two durations for the hand. However, no such differences was found in the torso. Third, matching the physical properties of a virtual object and the vibration frequency can improve the tactile experience. A higher frequency can be a good selection for metallic virtual objects, and the lower frequency around 40 Hz feel like rumbling or bumpy. Among 3 vibration frequencies, illusory penetrating sensation are elicited most effectively with 100 Hz at both body sides. Last but not least, after the major variables listed above are determined, one can choose a modulation function that presents the best penetrating tactile sensation. From our observation, a high degree gamma of polynomial generally provides good penetrating tactile sensations with clearly perceived passing through direction. This is the end of my talk. Thank you for watching it.